So I will first introduce the topic and the reasons why it is interesting and important to study geoneutrinos. Okay. Then we will go together through the first ideas which appeared to use geoneutrinos in order to understand the deep Earth. Then I will discuss how the expected geoneutrino fluxes are calculated. And then we will review the existing geoneutrino measurement, and we will look at the outlook of this new field. So our planet on which we are living is stacked with the energy. And we can see the demonstrations of this power in different occasions. It can be dramatic, as, for example, the earthquakes which hit also the region around the Borexino detector, which measured geoneutrinos. It can be relatively innocent and spectacular to watch it. That, for example, this explosion of the Kamchatka volcano, that can be fun to go to have a look and explore. And we can ask, from where is coming this energy which is driving these processes? And now we are going to discuss how can neutrino physics help us to understand this question. So the total integrated flux, heat flux, which is going out of our planet, was estimated based on the measurement of the temperature gradients along several thousands of the boreholes around the globe to be 47 plus minus 3 terawatt. Now, there are two main contributions to this number. So one part is coming from, is the latent heat from the time of the accretion, let's say. So it's the cooling of the core and the mantle. The other part is the radiogenic heat from the decay of long-lived radioactive elements. And exactly this part is what the geoneutrino studies can pin down. So geoneutrinos are electron antineutrinos from the decays of long-lived radioactive elements which are present in the Earth. In particular, the dominant contributions are the antineutrinos from the decays of the chains of uranium-238 and the thorium-232, and decays from the potassium-40. These particles are the only direct probe of the deep Earth. And as you can see from these equations, the released heat, the radiogenic heat, and the amount of emitted geoneutrinos are very well known. So in principle, by measuring the flux of the geoneutrinos, we can exactly get the radiogenic heat. Of course, in practice, it's more complicated, and we will review why. In summary, the Earth shines in antineutrinos with the flux of about 10 to the 6 per centimeter squared per second, which is a big number, but it's still 4 orders of magnitude less. That is the flux of the PP neutrinos coming from the sun and neutrinos. So neutrino geoscience is a truly interdisciplinary field. As I said, the main goal is the determination of the radiogenic heat, which is strictly connected just through the nuclear physics, let's say, with the abundances of the radioactive elements. But it is exactly the distribution of the radioactive elements inside the Earth which is making this field interdisciplinary, because both the prediction of the geoneutrino flux as well as the interpretation of the measurements in order to come to the main goal, this makes the things really complicated. Main goal of this field is this extraction of the radiogenic heat, but there are also other goals. For example, the measurement and determination of the uranium and thorium in the bulk Earth, it's very important in order to shed light on the processes of the Earth's accretion and formation. We can study mantle homogeneity or stratification processes, or we can test the ideas of additional heat sources in our Earth, as, for example, the idea of Herndon of the existence of the uranium-based georeactor in the Earth's core. What I would like to highlight that most of these goals had only little hope to be ever answered before geoneutrinos came on the scene. So now let's have a look on the first ideas concerning the expected geoneutrino fluxes and the possible detection techniques. So it was Gernot Eder from Gießen in Germany in 1965, so after Reines and Cavan detected reactor antineutrinos, who came with the motivation to study what we call today geoneutrinos, to a very particular reason, to find a heat source for the expansion of the Earth's radius, which to my best knowledge, it was not confirmed to be the true. Anyway, he estimated the fluxes to be about 100 times bigger than what we actually know that it is the reality today. He realized that the detecting of neutrinos emitted from potassium is almost hopeless. But he pointed out that detecting antineutrinos with the IBD interaction with water target could be possible. However, he did not make much discussion of the detection. It was much in more detail done by Marx in 1969. He also discussed more about the motivation as we see it today. He estimated the fluxes, but he was even farther away from the reality by 3 orders of magnitude. He studied induced beta decay on different targets, including the one which we are using today. And he mentions also the induced electron capture, so the resonant capture for monoenergetic antineutrinos. Then there was this paper in Nature by Krauss, Glechow, and Schramm, who really discussed it much broader way, both the geological motivation. They expect the fluxes much more realistic, they get much more realistic value. And they discuss the usage of different kind of targets for the radiochemical detection of geoneutrinos. And then came the first ideas about the use of the liquid scintillator detector. And in this moment, I would like also to recall the memory of Raju Raghavan, who was really the pioneering figure in this field. And I have had a chance to get to know him personally as a member of the Borexino collaboration, who came up with the idea with testing the reactor hypothesis through the detection of antineutrinos with liquid scintillator detector. And then in 1997, he published together with Stefan Schoner, Enomoto, Shirai, Suekane, and Suzuki, the paper about measuring the global Earth radioactivity using the multi-detector, that means Borexino and Kamland antineutrino spectroscopy. In 1998, it was the Rothschild, Mark Chen, and Frank Calaprice who also discussed this topic. So how do we calculate the expected geoneutrino flux today? In this matter, I have to introduce the concept of the bulk silicate Earth models. So these are the geochemical models which use different kind of inputs, which predict the total abundances of the elements, including uranium, thorium, and potassium in the primitive mantle, which is in the good approximation as the remixed crust and mantle, which differentiated from the homogeneous Earth later on. So in order to get the amount of these elements, and thus also the radiogenic heat in the mantle, what one has to do is to take the prediction of the geochemical model, pick one of the one model which exists on the market around, subtract the relatively well-known contribution of 7 to 8 terawatts from the crust, which we know precisely because it is here, we have the samples. Here are the works existing about. And then you get the span of 3 to 25 terawatts of radiogenic contribution of the mantle to the total 47 terawatt heat flux going out of the Earth. So it's a big uncertainty. Then how do we do expected geoneutrino signal calculation? So if you know abundances and distributions of uranium and thorium, it's easy. It's just an integral. However, we don't know these things with precision. And here I would like to underline the work of the group of Gianni Fiorentini and Fabio Mantovani in Ferrara, who pioneered in the early 2000s this kind of work. They estimated that it is very important to know the local geological composition in the area of few hundred kilometers around the experimental sites on the continental crust, which is rich in these elements. For the crust which is farther away, you can do some approximations. And for the mental contribution, you just have to, as I explained before, pick up the bulk silicated model, subtract the crustal contribution, and play around with the possible distribution of the remaining uranium and thorium. A huge amount of work has been done in predicting global, so for the whole crust, or the local signal for different experimental sites. It's really an enormous amount of work which has been performed. This is an example of the global map performed by these authors. And we can see that the total signal is expressed in the so-called TNU, which means terrestrial neutrino units. It means one event per roughly 1 kiloton of liquid scintillator per 1 year for a detector with 100% detection efficiency. And you can see the crustal, the dominant contribution is maximum 50 TNU in the region of Himalaya where the continental crust is doubled. So the signal is small and we need big detectors. For the mantle contribution, this is one hypothesis of the heterogeneous mantle, which is motivated by the observation of these large shear velocity provinces, which might correspond also to the compositional inhomogeneities. Even in this model, the maximum signal would be 10 TNU. So to measure mantle signal is even more challenging. An alternative approach in the estimation of the expected crustal signal is not through the study of the uranium and thorium contributions, but it's from the study of the heat flux measurement on the geologically stable regions. People as Jean-Claude Maréchal, Claude Jopard, Jarodsky have performed such studies, and here is an example of their result for the region of around the Sudbury mine, which is a very stable craton region, in which the heat flux between the crust and mantle boundary can be estimated. And you can see that comparing to the standard approach of the estimation through the composition abundances of uranium and thorium, there are some interesting discrepancies which could be tested by the measurement of future SNO experiment. So this brings me to the detection of geoneutrinos. Only 2 experiments has up to now measured geoneutrinos. There are both liquid scintillator detectors, radio pure, large volume, and placed in the underground lab. Kamland in Kamioka mine in Japan is at the border between oceanic and continental crust, and Borexino is on the other side of the globe on the continental crust, and this makes these experiments completely complementary. Kamland was built to measure reactor antineutrinos, while Borexino was built to measure solar neutrinos, so there is no IBD coincidence, and that's why Borexino was forced to, and succeeded in this, to get the extreme radio purity of the detector. It's 3 times smaller than Kamland. Kamland is about 1 kiloton. And at the beginning of data taking, Kamland has really a lot of reactor background because they've been measuring reactor antineutrinos. And in Italy, in Borexino case, there are no nuclear power plants. After the Fukushima disaster in March 2011, many reactors have been switched off. And currently, the signal to background ratio for Kamland is incredible 1. So I don't have to spend much about the structure of the detectors in this community, but as we know, that the scintillator target is in the core of the onion-like shell of the detector. It's viewed by the array of few thousand PMTs, shielded by the buffer region, and everything is enclosed in the water Cherenkov veto, shielding, serving both as a passive shield and an active veto for the remaining muons. The detection for the geoneutrinos is the inverse beta decay reaction. Because it is a charge current interaction, it's sensitive only to the electron flavor part of the geoneutrino flux. The signal is from the positron, And through the measurement of the kinetic energy of this created positron, we can directly get the information about the energy of the incident antineutrino. So it's the energy of the positron interaction, which then brings us to the higher level analysis in the geoneutrino case. And in order to pinpoint these geoneutrino interactions, we use the space and time coincidence with the signal corresponding to the neutron capture on hydrogen, emitting 2.2 MeV gamma ray. So this is the geoneutrino spectrum. This is per event. This is the kinematic threshold of the IBD of 1.8 MeV. Unfortunately, potassium is all below, so we don't detect it. And what we detect is the high energy tail of the uranium and thorium series, and you can see the endpoint energy of these two contributions is different. When you consider the IBD cross-section and you assume that the uranium and thorium abundances in the Earth is in such a ratio as in the chondritic meteorites, you get the shape of the expected geoneutrino signal. The main background to geoneutrinos are, of course, reactor antineutrinos. And among the main non-antineutrino backgrounds are cosmogenic backgrounds. In particular are the lithium and helium isotopes, which are decaying beta N. Also, fast neutrons could be a problem in shallower experiments. Accidental coincidences, and also alpha N reactions, especially if the liquid scintillo detector is contaminated by polonium-210, which is then the source of alphas. The first search for neutrinos has been done by Kamlan in 2005. It was published by Nature and beautifully described in a PhD thesis of Enomoto Sanshiro. It is really pioneering work. Unfortunately, the statistical significance of the result was below 2 sigma. These are the latest published results, both from the Borexino from 2015, detecting 24 geoneutrinos, and for Kamlan from 2013, detecting 116 geoneutrinos. Here the spectrum ends at 3 MeV. Here it goes to the end of the reactor spectrum to about 7 MeV. I would like to underline that really in the case of Borexino, we have just the geoneutrino contribution reactor, and the non-antineutrino background is invisible here. It's below one event. In case of Kamlan, we can see the geoneutrino contribution is this blue region. Then we have non-antineutrino background, and the white part are the reactor antineutrinos. Here is the summary of all published released measurements of geoneutrinos, both from Kamlan and Borexino, with the rough precision of the measurement, just divided the error, divided the mean value. You can see that we started from some higher error, and currently there was also, in 2016, was a preliminary update from Kamlan, presented by Hiroko Watanabe. And due to the low reactor antineutrino background, they really obtained very nice results, and we are looking forward soon for the published version of this result. Also in Borexino, we are finalizing the analysis, and due to the improved selection and increased fiducial volume, we will have the result with better than 20% precision soon. So what are the first geological interpretations? So I think what is very important is that, and the people sometimes forget that we measured geoneutrinos, we proved that it's possible to measure them, and the results are in the agreement with the expectations. Before, we did not know, these were just models. There could be huge amount of uranium and thorium somewhere deep there, but it's not the case. This we have already proved. We cannot, however, distinguish between existing bulk silicate Earth models and so on. We need more statistics. Uranium and thorium ratio is compatible with the chondritic ratio, which we assume in the bulk Earth, because we see it in the chondritic meteorites, and we see such ratios also in the solar photosphere. But also here we need more precise measurements. There are first indications of the measured non-zero mental signal. And the idea of Herndon about the active georeactor in the Earth's core was practically excluded. So what we want is bigger experiments with more statistics. We want multi-site experiments to test mental homogeneity or heterogeneity. And we need experiments in geologically particular locations. So what is the future? We expect soon updates from Borexino and Kamland. Snow Plus is coming on the scene in the very deep lab with low cosmogenic. They expect 30 to 40 geoneutrinos per year. Juno is expected to start data taking in 2021. And due to its large mass of 20 kiloton, it expects 400 geoneutrinos per year. And it has a possibility to measure within the first year the geoneutrino flux with 17% precision. Then Jinping is the deepest lab where will be constructed a 5 kiloton detector dedicated to the measurement of geoneutrinos and solar neutrinos. And it is at a very interesting region where the continental crust is doubled, so the contribution from the crustal geoneutrinos will be very, very high. My favorite is the son or daughter, let's say, of John Learned, would be the underwater detector Hano Hano. Was suggested with 10 kiloton, it would be movable, but why it would be the best one, in my opinion, because it would measure almost directly the mental contribution. The oceanic crust is simple, depleted, and in uranium and thorium and sin. So with this, we would just measure the mental contribution, but nobody wants to pay for it. That's the problem. So with this, I come to geoneutrino summary. The new interdisciplinary field of neutrino geoscience has been established. The collaboration is existing between the geologists and physicists. There is a conference series, Neutrino Geoscience, is 2005, and it was exactly here in Paris in 2015, where there was the last edition, and it should be time to organize a new one. Since 2016, there have been already 2 dedicated ISAP summer school about using particle physics to understand and image the Earth. Geoneutrinos has been observed, and the main results are in agreement with the average of the expectations, but we need next generation of experiments to really have geologically significant results. And I would like to finish with mentioning just the 2 challenges which are in this field. The first one is the detection of the potassium-40 antineutrinos, which are below the IBD threshold. It's very important. Another challenge would be to measure directionality of incoming geoneutrinos, which would help in distinguishing the horizontal crustal and the mantle geoneutrino coming from the more vertical directions. And with this, I thank you for your attention.
What about June and Hyper-K? Can they see this?
Not much, because the threshold. With the Cherenkov light for these energies, they have the threshold of, for the solars, 4 or 5 MeV. And the endpoint of geoneutrinos is about 3.
Is it that low? 3?
Yeah.
I thought it was 10 more.
No, it's the. You see, it's this is the end point of geoneutrinos. These are the reactor antineutrinos which extend, but which for geoneutrinos it's good in a way, because if you know the spectrum of the reactor antineutrinos and you don't have a non-antineutrino background, as in case of Borexino, you just fix your reactor component in the spectral fit, and then the rest are the geoneutrinos.
I'll just make an unpaid advertisement. The Hano Hano idea is being sort of revived in Japan, where we've been getting going on something called Ocean Bottom Camland. There's an organization in Japan called Jamstack, which builds very large ocean engineering projects, and there's some interest there.
That's fantastic news.
Yeah, but if anybody's interested, they should talk to the people in Sendai, Kunio Inoue, and Bill McDonough, and Hiroko Watanabe, and myself. I don't know if it's going to succeed, but we've been breathing a little life into it.
Okay, thank you for information.
A stupid question. Why is the neutrino background so high in Italy where there are no nuclear reactors?
It's not high, it's small. I mean, the closest reactor is about 400 kilometers from Slovenia, and then the mean pass weighted by the thermal power plants are the reactors across the arc of the Alps, like so from Germany, France, and so on. So it's small. I mean, comparing, because be careful, this background is then continues up to this bump. So here in this plot we see just this part up to 3 MeV.
The new measurements in Japan will be different completely with the background situation.
I have a backup slide from the Hiroko talk. So this is the 3 phases of the Kamlan from the published paper from 2013. You can see that in the first period they had, here it goes up to the endpoint of reactor antineutrinos. The blue is geoneutrino, white reactors, and these are alpha N and accidentals. So you can see in the first phase up to the 2007, the geos were really a small part of the spectrum. Then they did the extensive purification, and this colorful part diminished. And after the Fukushima reactors, the disaster, the contribution of the reactor spectrum is really extremely suppressed. And in addition, here, this is from 2016, from the talk of Hiroko Watanabe. This is the spectrum updated after the Fukushima until 2016. So she told me that within half a year they expect the publication, and it will be even nicer because there are 2 more years of data at least.
Could you please go back to your summary slides? And my question is if you can elaborate a bit more on the challenge number 1, like meaning if we were to observe these potassium-40 neutrinos, geoneutrinos, what would we learn in addition to what we have already?
So up to now, I mean, since the goal is the measurement of the radiogenic heat, up to now we measure uranium and thorium, and in order to compare to the radiogenic heat of which is measured, this upper limit of 47 terawatts, you have to invent something for potassium, right? So what was currently done, because of the plots, for example, like this one, this is the correlation between the isotopic ratios with respect to silicon in carbonaceous chondrites, and in the solar photosphere, it's perfectly correlated. So we believe that something like this should be valid also in the Earth. That's why it's important to measure, for example, thorium and uranium ratio in the feed in which you leave these 2 contributions free in high statistics experiment. So if you measure uranium and thorium, you confirm that it's in the chondritic ratio, then you can kind of feel free a little bit to assume chondritic ratio also for the potassium. But, and I go back to this plot, this is how much volatile these elements are. So this is the condensation temperature. It's from Bill McDonough paper of different elements and their abundances in Earth. Uranium and thorium have high condensation temperature, so they are refractory. They remain in the Earth from the creation. Potassium is more volatile. So it would be important to really get the radiogenic heat to measure also this contribution.
So any other question or comment?
Yes, my name is Paola Antolini. I am a scientific journalist and an anthropologist. So thank you for your bright presentation. I am in the European program Gender Equality. So I am glad to see finally a woman also in the afternoon, and a bright one. So I would like to know, from the anthropological point of view, how many persons are working on this research? And what would be, in your opinion, the social impact for the civil society? Because this is also one of my responsibilities, the social impact of all this beautiful science. Thank you.
So you mean in general in neutrino physics, or
Yes.
Yeah? So I spent 10 years of my career in Italy. I was there from 2005 to 2015, and it was really great to see that, for example, in Italy, I still don't understand the reason, so maybe you can explain this to me. There are many women in physics in Italy. So, for example, in Borexino, also in Geoneutrino studies, we worked a lot on the first release with Sandra Zavatarelli, my colleague in Borexino, so she's also a woman. So this is something which I don't have the answer. Then I think that, for example, when I studied in Slovakia, I'm originally from Slovakia, we've been very little women, maybe I would say 3 from 30 total persons, but I never felt, I personally was always convinced that I want to do this. And there were no problems. I never had any feelings that I cannot do it because I'm a woman. And it was impressive to hear today, for example, things like women could not enter the underground lab or something like this. I fortunately never experienced something like this. So, but I think it's very important to encourage there where women could have still problem today, in the countries where this could be still the problem. And I can say, for example, the school I have mentioned here, this ISAP school, in this year we organized it in Ferrara in Italy. And we had many young girls coming from the Arabic countries coming to this, so it was very nice to see it there.
And for the Geoneutrino, yes, the Geoneutrino research, I like this image of Himalaya that you show because I have been there working. What benefit could bring for the civil society, let's say? Even if it's a beautiful knowledge, all that, if there is something more being a geoneutrino.
Well, I think this is a more general question. I mean, like some people are telling, okay, bread will be not cheaper if you will understand. But as we know, all the time when you have it's like a circle. The basic science is maybe driven by curiosity and will not directly or immediately bring to have the bread cheaper. But it can help in practical applications. For example, general relativity, oh goodness, few people in the world can understand it and so on, but today the GPS which we use is using the corrections which is based on the general relativity. And vice versa. The application, the development of the technology is helping us to construct new detector. And for the detectors which are really at the top notch of the technology are also driving the development of this new technology and then so on. So it's a closed circle, and I think it's important that, especially today, where often I see that the basic science is somehow having difficulties to survive, but I think it's important to, at least I try, to to help the curiosity-driven science survive, because I think without that, the science will be dead.
Okay.